Okay, so we know that the work done by a non-conservative force is equal to the change in mechanical energy. Um, so we can think of our non-conservative forces basically being anything other than friction. Will suffice for now. And so this is, the change in our elastic potential energy, the plus the change in gravitational potential energy, plus the change in kinetic energy, right? The change in all these energies. If we have no non-conservative forces, then there wouldn't be any work done by the non-conservative forces, right? And so this whole thing would be equal to zero. And so then if the work done is zero, then the change is equal to zero, right? And so then we'd have to say that the final mechanical energy, because this change is, this is like ME final, or maybe I'll call ME at position 2. That's like our final, minus the mechanical energy at position 1, that's our initial, is equal to 0, right? Or I could say here that the mechanical energy at one point, at position 1, is equal to the mechanical energy at position 2. So the mechanical energy, as long as we don't have any non-conservative forces acting and doing non-conservative work, then the mechanical energy at one point is equal to the mechanical energy at another point. Now, within that, there can be different forms of mechanical energy, right? There can be elastic potential, there can be gravitational potential, and there can be kinetic. Then later on, we'll see rotational kinetic energy as well. But the sum of all of these three forms of mechanical energies must always be the same at every point if I have no friction. So returning to the roller coaster example from the videos, we have something like this where we have a mass up here and it's up at position 1, and there's some mass up here, it's 50 kilograms, and it's allowed to move down all the way down here, and then it goes through the loop, etc. And it's 4 meters high off this kind of this reference plane down here, and they gave us a reference plane, which they dimensioned all their heights off of that, and we can call this our datum, right? So this is just a reference where the height is equal to 0. Okay. So if we assume here that whatever this object is, it's going to go through the loop-to-loop, we assume that it starts out at rest up here at the top. So let me get rid of some of this. So if we say that, all right, the velocity at point 1 is equal to 0, we'll say that it starts out at rest, and we can go from there. So the velocity is equal to 0, and then the kinetic energy, which is, remember, Ke is equal to 1/2 mv squared. If the speed is 0, then the kinetic energy is also 0, right? So we have 0 kinetic as well. And the potential energy, well, it doesn't have any spring. We could, if we wanted to make it more exciting, we could put a spring here, compress, something like that, but there's no spring here. So all we have is gravitational potential energy now. And the gravitational potential energy, remember PE grav, this is equal to mgh. And so the height is 4 meters, the mass is 50 kilograms, and so then our potential energy here, this is just going to be 50 times 9.8 times 4 meters. And that's 1,960 joules. So we have here 1,960 joules. That's how much potential energy we have. Now the mechanical energy, this is the sum of all of these: elastic potential, gravitational potential, and kinetic, right? And so since kinetic is 0, also elastic potential is 0, it's just the same as our gravitational potential. So this is 1,960 as well. And then we can move on to point 2. And I'm going to get rid of this J just for clarity here. So these are all in joules. And then at point 2, we can use this information that we had from point 1 and the fact that this is frictionless. We're told that this roller coaster is frictionless. So we can use kind of our solution for stuff at part 1 to help us out with part 2. Namely, we can actually use this fact that the mechanical energy is constant, right? As long as I don't have any friction all throughout here, then the mechanical energy is constant. So this is always 1,960 joules. So that's the same at all these points because we have mechanical energy conserved. So it doesn't change. Now at point 2, we're given a new height, right? We're given a new height here. This is 3 meters. And so at point 2, we can just use mgh there and get our potential energy at point 2, which comes out to 1,470 joules, just mgh. And so the kinetic energy, therefore, must be the difference between these, right? So we can find the kinetic. Our kinetic here must be equal to the mechanical energy minus the potential energy. And so this is going to be this 1960 minus 1470. So that comes out to 490 joules. So there must be 490 joules of kinetic energy because, you know, that's what we needed in order to have the potential and kinetic add up to 1,960. Now we can use this to find out what the speed is as well. So now that we know the kinetic energy, we can find out what the speed is because the speed is related to the kinetic energy. So I know here that 1/2 times the mass times the speed squared is the kinetic energy. And so then this is 1/2 times the mass was still 50 kilograms times the speed squared is equal to 490 joules. And so from this, we can get a speed is equal to 4.43 meters per second. As long as I'm dealing with joules, kilograms, meters, all that stuff, we'll have our standard units, meters per second. So the speed is 4.43 meters per second. So based on the height alone, based strictly on how high it was when it started out and how high it is now, I can tell how fast it's going. And basically what's happened here is that there was potential energy here. There's some potential energy as it went down to here, that 1 meter. That potential energy is converted into kinetic over here, right? And that's how I got the 4.43 meters per second. Okay. And then at point 3, we have, well, what's the height over here at point 3? It's right there at our datum. Now it could be, the height really could be 1,000 meters or something, but we've chosen a reference height to be, this is our datum where the height is equal to 0 here, and point 3 is right on that datum. This makes it very convenient for calculating our potential energy there. And so the potential energy at point 3 is equal to 0, which then means all the energy is kinetic, so 1,960 joules of kinetic energy. So then going through the same thing, the same way that we found the speed at point 2, we can find the speed at point 3, and we end up with 8.85 meters per second at point 3. And then at point 4, we're given, they changed it up on us a little bit here, we're given a speed here, and then we're asked to find the height. So it's just a slight change, but we can take care of that. So given that we have 6 meters per second then our kinetic energy is equal to 1/2 times 50 times 6 squared. And so that is equal to 900 joules. And so then the potential energy must be, everything else to make it up, right? So this is 1,060 joules. And then, finding out, well, we can find the height based on knowing how fast it's going. Find the height over here. We can do this by saying, well, I know that mgh, this is my gravitational potential energy. This is equal to my potential, gravitational potential, which is 1,060 joules. And so then solving this, the mass is 50 kilograms, g is g, and so then we end up with a height of 2.16 meters for a height. And so so we were able to calculate a whole bunch of information on this roller coaster, and this all assumed that it was frictionless the whole way along here, right? So we had the entire path frictionless all along here, so that way there was no work done by some non-conservative force. And it really doesn't even have to be frictionless. It can just roll on there, and then we assume that there's no friction associated with that rolling. So let's say what we did here is we said all through this the coefficient of kinetic friction was equal to 0, or it was just had rolling friction. Let's say, what if we go a little bit farther? What if we then come over here, and let's say that it hits a rough patch after, because it needs to come to rest, right? So let's say there's something over here and there's a rough patch. So the coefficient of kinetic friction here is equal to, I don't know, we'll call it a half, 0.05. And we want to know how far will it travel. So we have this object there, and we want to know how far is it going to travel along here. What's this delta x? So now work is being done by friction, right? So mechanical energy is no longer conserved. And so we can still use the work energy theorem to find out how far it traveled, right? Really, this conservation of energy came from the work energy theorem, really. If you go back and look at this, this was all, it came from the work energy theorem. So we'll just do that now, where we actually have work being done by friction. So I'm not going to take the time to draw the free body diagram of this whole thing here. Well, actually, maybe I should. Here's the free body. Here's like a block over here as it's sliding along. Had some initial velocity, which we could actually find out what that initial velocity is. We could just, it should be the same as 0.3 actually. This initial velocity is the same as 0.3, 8.85 meters per second, because it's at the same height, right? So it'll have the same speed there. So it's cruising along, and there's some forces that act on it. There's a weight going down like this, there's a normal force like this, and there's a frictional force like that. And it's going to travel some distance over here, delta x. Okay, so looking at this, summing the forces, I know I have no coordinate system here. I know I have no acceleration in the y direction, so this leads me to the normal force is equal to the weight because it's on a flat surface. And the frictional force is the coefficient of kinetic friction times the normal force. So we get here, the frictional force is equal to negative mu k mg is what this comes out to. And so the work done by friction is equal to the frictional force times the distance, right? I'll call it S. Actually, maybe I should just call this S as well. And so then the work done by friction is going to be negative mu k m g s. And this work done by friction is going to be equal to, I don't have any, there's no spring that it hits or anything. There's no change in height. So the only type of energy I have to change is kinetic energy. So the work done by friction is going to be the change in the kinetic energy. Okay, so that's going to be equal to, I guess I can call this, I can give it some new points here. I can say this is 0.5 and this is 0.6 where it comes to rest. And so then this is my change in kinetic energy from 5 to 6. So this is like the kinetic energy at 0.6 minus the kinetic energy at 0.5. Okay? Of course, then we know that it comes to rest at 0.6, right? So this is equal to 0. And this comes out to negative mu k m g s is equal to negative 1/2 m times v5 squared. You know, if I wanted to as well, I could have actually just said this is negative of the kinetic energy at 5. If you come back here, so this is just, you know, the kinetic energy at 5, which is actually the same as the kinetic energy at 3, which actually, even then, this is, because this is where my height is 0 at 5, this is just all of the energy. It's the total mechanical energy. This is actually just negative 1,960 joules. So I could just plug that in there, but I'll do it in terms of the speed as well. Because that's very much like what we did with the it was like a car that slammed on its brakes and skidded to a stop, and this is basically the same thing. So the mass cancels out on both of these, and we could actually see that the distance it travels, S, would be equal to v5 squared over 2 mu kg. I think this is what we came out to with the car. Or this is equal to, if I do it in terms of the kinetic energy, this is just equal to 1,960 joules divided by mu k mg, right? And plugging in that we had 1/2 for mu k, and we had 50 kilograms for m and 9.8 for g, we get this distance it travels, S, is equal to 8 meters. So that's the delta x we were looking for in the first place. It was just a little bit easier to go with this kinetic energy route instead of, I could have found the speed at 5 first, and it would be exactly the same thing either way. So that's conservation of energy, and also the work energy theorem kind of put in there for both.